This is the Ivankiv district of Ukraine in Eastern Europe. Once part of the mighty Soviet Union, it became a world of ghost towns and hastily abandoned cities. It's one of the most radioactive regions on the planet, with over 2,500 square kilometers deemed uninhabitable. All the result of one of the world's worst engineering failures. In 1986, a routine safety test went devastatingly wrong at the Chernobyl nuclear power plant, and a series of explosions spread clouds of deadly radiation across Europe and beyond. Safety teams rushed to cover the wrecked reactor with a rapidly constructed concrete box. The emergency measure was a temporary fix to contain the danger. But now, 30 years on, the structure around the damaged reactor is at serious risk of failure, threatening the whole of Europe once again. So some of the greatest engineering minds from around the world have come together to design a unique solution. A giant protective container known as the new Safe Confinement.
It's enormous. It's 108 meters high. If you're British, it would cover St. Paul's Cathedral. If you're American, it covers the Statue of Liberty. If you're Italian, it would cover the Colosseum. And if you're French, it's 3 times the weight of the Eiffel Tower.
This is absolutely a one-of-a-kind structure. It is, in fact, the largest man-made, movable land structure ever built. Weighs 36,000 tons, 257 meters wide, and has a length of 160 meters. It's huge, and no one has ever built anything like this before.
But this is more than just a building. It's a machine designed to facilitate one of the most important ongoing engineering projects in history. Dismantling and cleaning up the destroyed reactor. A task which could take at least 100 years. Designed to withstand a century of bitterly cold Ukrainian winters and scorching summers. A 25,000-ton steel frame supports the giant metal panels which slide over the existing shelter, creating a barrier to stop radioactive dust from escaping. With an uninterrupted floor area of 43,000 square meters, it's big enough to park 8 jumbo jets. Simon Evans is one of the project's overseers.
The role of the new Safe Confinement is twofold. Firstly, to confine the old reactor so it can ensure you minimize any future releases of radiation. And secondly, to provide the infrastructure to start taking the old structure apart and put into a safe and secure long-term condition, because 96% of the lethal radioactive inventory is still sitting inside that building, so it had to be secured.
Heading up the team of project managers is Mac McNeil.
The structure that was built over the reactor was constructed in 6 months following the actual disaster. Because it was such a radioactive environment, the people who worked on it could not use traditional construction methods. So the structure itself was never a very stable structure.
To be able to dismantle it, the old radioactive building must be entirely covered. But this provides a seemingly impossible engineering challenge on a scale never attempted before.
I think this is one of those projects that people thought could not be done.
So how do you build a self-supporting structure capable of enclosing a volume of 1 million cubic meters? The answer lies with techniques pioneered almost a century ago. Once upon a time, airships were seen as the future of aviation. Mechanical engineer Dan Dickrell is boarding a 21st century blimp in search of an historic key to the seemingly impossible challenge faced at Chernobyl.
Oh, that's a strange sensation of just like lifting up. We're just floating.
When it comes to blimps, size matters. The bigger it is, the more weight it can carry.
Aircraft of this size present a big problem. It's huge. Where do you store it? Where do you build it? And to solve that big problem would require a very innovative solution.
That solution would come from Czech-born airship pioneer Carl Arnstein. To build and house his mighty machines, Arnstein designed an unprecedented new hangar and built it in Akron, Ohio.
Oh, this is it. This is the Acron Air Dock. It's built in 1929. At the time, it was the largest single room on Earth. It's a massive structure. You really don't have a sense of it until you get in here.
The Acron Air Dock is 360 meters long, 100 meters wide, and 65 meters high, with a floor area of 36,000 square meters.
We could fit the Statue of Liberty from side to side and the Empire State Building from end to end with just a little bit sticking out. The reason why that's possible is because the air dock's volume is entirely usable. There are no internal support columns. It makes this a fabulous space.
It's this type of uninterrupted floor space that the engineers at Chernobyl needed to build to contain the reactor. So how did Arnstein achieve it?
The roof is supported by 11 parabolic steel arches. This keeps the floor completely clear of internal columns. This was a massive leap forward in long-span construction.
But the vast size of the hangar presented a serious problem to its structural stability. Steel reacts to changes in temperature. On a small scale, it's hardly noticeable, but in the then world's biggest room, it could have catastrophic consequences.
So when the sun hits the steel structure, it causes it to expand. So Arnstein designed the building to breathe. So this is the leg of one of the arches. Down at the bottom, there's a foot. Now the footer is floating. It's not rigidly connected to the ground. And this is the key innovation that allows the building to expand and contract as it heats and cools. If it was rigidly connected to the ground, the building would essentially rip itself apart.
But that wasn't the only problem caused by a hangar this big.
The rumor was this building was so large it'd create its own weather system. The temperature difference between inside and outside would cause clouds to form and condensation to build up on the steel structures, raining down water on the workers below. To solve this, they installed massive window banks to help equalize the temperature between inside and outside, solving the rain and weather problem. The air dock was a masterpiece of long-span building engineering, and the techniques used in its design and construction, which seemed radical at the time, have become commonplace in constructing a building of its size.
Engineers at Chernobyl must adapt this concept to create something big enough to contain the decaying carcass around the reactor, or they risk another nuclear disaster. Mac McNeil, the lead project manager, has clearance to enter the restricted area near the failed reactor.
Now what you're looking at here is the structure that was built over the reactor very hastily in 1986, after it blew up. Over the last 30 years since the accident, the structure itself has continued to deteriorate You can see a lot of corrosion on it, showing the effects of weathering. And when you think of it, how huge this structure is, the dimensions of this new safe confinement are really spectacular.
Like Arnstein's air dock, the structure of the new safe confinement relies on the power of the arch. The metal framework is made up of a series of 16 arched trusses, standing at over 100 meters high.
Those steel structures, very, very large, they are all bolted together. There's no welding on it. And there are over 600,000 bolts that hold it all together. It's a very, very complex structure, but it has to be because of the size and the overall weight of the arch. When I arrived at the project, my first reaction when I walked under it was how huge this thing is. I mean, how tall, how wide, how long. It was a feeling that got your attention.
And unlike most other construction projects, failure to complete it puts lives at risk.
It's an immensely time-sensitive project because the longer you delayed, the more dangerous it became. Careful around here.
As the head of the project for its financiers, Simon Evans has special security clearance to go even deeper into the old reactor complex, to the heart of the disaster.
It's an enormous facility and very, very complex and very difficult to find your way around.
Security's tight due to the unspent nuclear material still present. The amount of time he can spend here is carefully controlled.
Judgments are that you have around 200 tons of material sitting inside Unit 4, inside the sarcophagus, which is probably about 10 meters to our right, fortunately through lots of walls of thick concrete. This is the heartbeat of the old reactor, the control room. The job of the controllers was to monitor constantly the power in the reactor to make sure the levels were stabilized. And what happened at the time of the accident was they lost control of the reactor. It was certainly the worst ever uncontrolled release of radioactivity in the history of nuclear power, and many, many times worse than Hiroshima. So I find this a very haunting place, to be honest, almost a monument to the importance of doing things safely.
Designing this vital structure is one thing. Building it in a nuclear disaster zone is another.
Working in this environment presented immense challenges for us. The biggest challenge, of course, is radiation.
And in the race to prevent another catastrophe, a seemingly impossible engineering challenge.
Once the top part was built on the ground, the problem was how to lift it.
The new safe confinement in Chernobyl, Ukraine. 10,000 people from 30 countries are working on the design and build of this vital structure, which will protect Europe from leaking radiation. Simon Evans is one of those running the project.
The new safe confinement is the world's largest land-based movable structure and probably constructed in the world's most contaminated place.
Following the 1986 accident, almost 100,000 people were evacuated, and over 2,500 square kilometers around the plant was declared an exclusion zone.
Working in this environment presented immense challenges for us. The first thing we had to do was clean the site, and then we had to make sure that we had all sorts of support facilities in place to enable many thousands of workers to come in over many years. The biggest challenge, of course, is radiation.
Radiation levels vary around the Chernobyl site. Higher doses of radiation for extended periods of time can be fatal. This means that time workers spend in the most radioactive places has to be carefully monitored. Something project manager Cyril Fargier has experienced firsthand.
The difference of radiation level between this place and really nearby the reactor is huge. To give you an idea, here a worker can work the whole year and not reach the limit. Whereas very close to the reactor, working 1 hour, we would reach the yearly limit.
The solution the team came up with was to build the structure away from the reactor. They identified an area of less radioactive land and planned to carry out the main construction here, then move it into position over the reactor. But even here, the time the workers could spend on site was limited. So the decision was taken to construct the enormous roof section at ground level.
The obvious advantage of erecting on the ground is it's much easier in terms of productivity to work close to the ground, whereas working at 100 meter high, it makes a big difference.
But by solving one problem, they created another.
Once the top part was built on the ground, the problem was how to lift it. The heaviest section was around 8,000 tons.
With traditional cranes ruled out on safety grounds, could the groundbreaking pioneers of the past provide a solution? Physicist Dr. Andrew Steele is in Munich, Germany, looking for answers that may help the team in Chernobyl. Almost 50 years ago, the city was preparing to host the 1972 Olympic Games.
Wow, check this out. At the centre of that Olympics was this almost 70,000-seater Olympic stadium, draped in this incredible cable net structure. At the time, a cable net structure this big had never even been proposed, let alone built. And the scale of this thing is just overwhelming.
436 kilometres of steel cables were strung between 58 steel pylons to support a huge canopy composed of 8,000 plexiglass panels.
Although from down here it looks like this roof is just floating over the seats, making it look this effortless is actually a huge engineering challenge. The roof was constructed in sections, and each one of those sections weighs well over 1,000 tons, presenting engineers with a problem. The plan was to construct those individual roof sections down on the field there, and then lift them up into position once they've been completed. And this presents quite literally an enormous challenge if you want to try and do it using a crane. You'd have had to position that crane outside the stadium, and as you can see, that means it would have had to have been absolutely huge. Engineers were going to have to devise a radical solution, which had never been tested at this scale.
Just like the engineers at Chernobyl, the German team needed to find a way to do some heavy lifting without using cranes. In the 1930s, renowned French engineer Eugène Freyssinet pioneered the use of hydraulic jacks as part of his methodology to pre-stress concrete to build longer bridges. The team in Munich had a theory that the hydraulic jacks that Freyssinet used to apply tension could also be used to lift such an enormous weight.
Engineers decided to use an adapted and relatively untested version of Freysinet's system, known as strand jacking. This was a bold move. Strand jacking had never been used for a project of this size.
With the opening ceremony of the Games looming, in June 1971 the engineers held their breath as the new technique was tried for the first time on this grand scale.
In total, 139 strand jacks were used to lift each of these sections of roof into place. And the way that these jacks work is they've got a couple of different anchors or wedges. One is fixed at the bottom, and that's going to be represented by my right hand here. And the other at the top is mobile. It's attached to a hydraulic ram, and that's going to be my left hand. So if I want to lift that weight down there, the first thing I've got to do is release this anchor at the bottom. Then the hydraulic ram does its stuff. And then when that gets to the top of its stroke, the clamp at the bottom grabs onto it again, which then means the hydraulic ram can move down, grab on, and then repeat. A great advantage of this strand jack system is that you can use them in conjunction with one another. So if you want to lift a heavier weight, you can use loads of them together in tandem to get them to do exactly the motion that you need.
Once completed, the enormous stadium roof covered an area of 74,000 square meters, at the time making it the largest cable net structure in the world.
Sat here, you can really see the genius of the design. It's an absolute engineering marvel. And today, strand jacking has a vital role in the world of heavy lifting. It's a remarkably simple solution, but it's an incredibly effective one.
But can the Chernobyl engineers, racing to prevent another radiation leak, use this technique to solve their giant problem? How to raise the roof?
So the optimized solution that we chose was to design and fabricate special lifting towers, and on top of each tower we install a platform with jacks.
With the strand jacks positioned on top of the lifting towers, cables with a high tensile strength are run down to the roof section. When powered, the jacks pull these cables, lifting the 8,000-ton section of roof.
Each jack had a capacity of a maximum 900 tons, and we had over 40 strand jacks activated simultaneously to make this operation.
A computer-controlled system ensures this crucial maneuver is pinpoint accurate.
All the 10 lifting towers lift the structure in an evenly way, okay, very smoothly. So we had the tolerance and accuracy every point within a few centimeters. So, but to get this accuracy over 260 meters, that's a very high precision.
The next sections of the arch were attached to the roof using giant hinges, and the whole thing was jacked up even higher. Once it had topped out at 108 meters, it was time to repeat the whole process for the second part of the arch.
There is excitement when you start an operation like this. You're even more excited at the end of the day when the mass has reached its altitude and is secured and everybody is safe and we have completed on time. It's totally a unique engineering work.
The framework was now taking shape, but the team still had some serious challenges ahead.
It was the most complex and precise engineering ever envisaged over such a site.
And they were battling against the clock to prevent another disaster.
Timing was critical to get the reactor covered. The concern was that it could collapse.
In the Ukraine, a race against time for the international team who've united to build the incredible new Safe Confinement to contain the damaged leaking reactor at the Chernobyl nuclear power plant. Costing over €2 billion, the giant arch is large enough to completely contain London's 96-metre-high Big Ben. Mac McNeil heads up the project management team.
Timing was critical to get the arch in place, get the reactor covered. It is not a stable structure, and ultimately the concern was that it could collapse. Of course, that could release another cloud of radiation, which no one wanted.
However, before the mighty arch can be moved over the reactor, the structure has to be clad. But finding a suitable material isn't easy.
We need a material that will last 100 years because the arch has a mission now, which is to do the deconstruction of the shelter. And that process could conceivably take a very, very long time.
They need something capable of containing some of the most lethal materials on Earth, and that would last a century of extreme conditions in this radioactive wasteland. For as long as man has been building, He's wanted to protect the results of his labours from the elements. The Egyptians applied a liquid membrane to the pyramids to try to protect them from the waters of the Nile. The other method is to add a protective layer on top of the structure, such as straw, tiles, or cladding. But all of these have a limited lifespan. However, something more enduring was on the horizon.
This is incredible. What a breathtaking view. The New York City skyline. It's so exciting to be up here in the city that I live in.
Professor Eric Lima is discovering how a case of one-upmanship led to a major innovation that could help engineers in Chernobyl.
In the 1920s and the 1930s, the city was gripped by skyscraper fever. Architects and engineers were outdoing themselves to try to build the highest buildings. I like to think they had drafting tables and they were drawing and they were saying, let's go higher. Why? So that they could be the highest in the United States and the highest in the entire world.
At the southern end of Manhattan, 40 Wall Street was under construction and looked set to become the world's tallest building. But just over 8 kilometers away in Midtown, automobile tycoon Walter Chrysler had other ideas.
Okay, what you see is the really cool, iconic building is the Chrysler Building. It was designed by William Van Allen, right there. The most iconic building, in my opinion, in New York City. Such a cool building.
But it wasn't on course to be crowned the world's tallest.
But Van Allen, he had a plan. Secretly, he obtained a license to bring a long, tall point, a needle, that he was going to put on the top of his building. But the problem was, it's going to be exposed to all the elements. Rain, wind, sleet. How do you make sure it doesn't rust?
It's the same problem facing the engineers in Chernobyl. For his solution, Van Allen turned to a new German innovation. In 1911, metallurgists Philipp Monartz and Wilhelm Borchers built on recent advances in non-corrosive steel used in cutlery to create an architectural version of steel almost entirely resistant to the elements.
So this scrubby is made of steel. The main component of steel is iron. Now, when the iron is exposed to oxygen in the air and moisture, there's a chemical reaction. That reaction makes iron oxide, otherwise known as rust. Monartz and Borchers discovered that by adding other elements, most importantly chromium, to this mixture, they were able to make an alloy that was much more resistant to corrosion than anything that had come before. Today, we call that mixture stainless steel. To prove just how resilient this material is, I've set up a little experiment here. Here's our steels, regular steel, stainless steel. We're going to replicate what decades of corrosion could do in just a few minutes.
The two versions of steel are soaked in vinegar for 2 minutes, and then to activate the simulation, they'll be placed in hydrogen peroxide.
All right, here we go. We're going to move them over. First, we're going to move the regular steel into the hydrogen peroxide. Then we're taking the stainless steel and bringing it into the hydrogen peroxide. And almost immediately, you can see the rust forming and you see streams of it coming off. You can see the reaction taking place. That's rust, that's iron oxide. It looks totally gross, actually. And on this side, crystal clear stainless steel.
The chromium added to the alloy reacts with the oxygen to form a film a few atoms thick. This protects the material from other oxygen atoms contained in rainwater, which would react with the iron, causing rust.
Monartz and Borchers discovered a metal that would go on to revolutionize the world.
Days before the grand opening, William Van Allen's spire, clad in this cutting-edge material, was erected on top of the skyscraper in just 90 minutes, crowning the Chrysler Building as the tallest in the world, pipping 40 Wall Street to the post.
When the Chrysler Building was being constructed, stainless steel as a material was almost completely untested architecturally. And yet, when you look at it, over 80 years now, it's completely withstood the trials of time. Today, that metal influences almost every part of our daily lives.
In Chernobyl, engineers are putting stainless steel to an even greater test. Protecting the world from another nuclear disaster.
So there are a little more than 87,000 square meters of stainless steel covering the exterior of the arch. That's why you see the shiny appearance of the arch when you look at it. The interior is also covered in stainless steel. We don't want this cladding material to deteriorate.
Sandwiched between two giant spans of stainless steel are multiple layers of other materials, all carefully chosen to help contain the radiation. But getting the equivalent of 12 football pitches of gleaming stainless steel onto the outside of a 108-meter high arch isn't easy.
The material actually was put in place using workers that we called alpinists because they had to be in full, almost mountaineering gear, suspended from the roof of the arch to put all these in place. They're absolutely mind-blowing.
With the crucial protective cladding in place, it's time for the most difficult part of the operation. But how do you move such a vast building in some of the most radioactive conditions on Earth? It's a huge moment for all involved, including Simon Evans.
This is the most unique part in many respects because along this beam, 36,000 tons of steel was slid over a destroyed nuclear reactor. It's hard to imagine it now, but it was the most complex and precise engineering ever envisaged over such a site.
If the old reactor building is disturbed, it would have catastrophic consequences. So it's essential this runs smoothly. Project manager Cyril Fargier is on hand for the operation.
So you can see here the skidding beams. On these skidding beams, we had a Teflon pass. On top of it, we had what we call the skidding shoes with a stainless steel interface, which allow a very small friction coefficient when we were pushing the arch.
But even with Teflon-coated skidding beams, it still takes a lot of force to move 36,000 tons. That force comes from a technology already used to lift the structure, hydraulic jacks.
So we had the jacks which are pushing horizontally, and also there was jacks perpendicular to the beam in order to monitor and to compensate any slight deflection of the beam.
In late 2016, the operation begins.
Watching the process was surreal in many respects because you could look at it from a very micro level and you could see the pistons moving very slowly and the whole arch seemed to object to moving because the noise it was making was like 10,000 fingernails on a blackboard. Yet when you looked up and saw this enormous structure over, did you really sort of start to feel the immense engineering that was in these pistons pushing?
Basically, we were doing up to approximately 100 meters per day, but sometimes less. It's not a race. The objective was to do it in safety and in quality, and not to create any stress in this huge structure.
As the structure approaches the old reactor building, it is the tensest moment of the operation. Carefully designed cutouts ensure the end wall clears all the protrusions from the reactor roof.
So when the arch reaches final position, we were able to complete the enclosure.
After 7 days of painstaking skidding, the structure's in its final resting place.
Sliding the arch was nerve-wracking, but when it had reached its final position, I'll confess I did feel a little bit emotional about it because it was such an epic moment.
It's extremely exciting because I believe right now in the world there is no such a project. So amazing in terms of size, dimension, challenge.
But the team still face the biggest challenge yet in their quest to put right what once went wrong.
This is where all of the action occurs, taking apart a structure so that you don't cause a collapse, which would then release contamination.
Just how do you dismantle the most radioactive building in the world? Ukraine, the heart of what was once the USSR. It's taken 8 years of construction, with 1,200 workers on site every day, to create the new Safe Confinement, the largest land-based mobile metal structure on Earth. Capable of withstanding temperatures as low as -43 degrees Celsius and wind speeds of around 300 kilometers per hour, this almost impenetrable barrier stands between the failing nuclear reactor and the Earth's atmosphere. But it not only encloses the reactor, it's also designed to dismantle it.
Inside the arch, there are 2 bridge cranes that go forward and backward across the whole length of the arch.
The 2 96-meter-long bridge cranes move along the east-west axis. Hanging from them are 3 tool platforms, which can move along the north-south axis. This enables tools to be remotely maneuvered to anywhere in and around the old reactor.
What we have here is the robotic mobile tool platform, and from this platform will be hung about 10 different tools that can cut, grind. There's some vacuuming tools, cut grabbing tools. So this is really the workhorse of the whole new Safe Confinement, because this is where all of the action occurs. In a sense, it's taking apart a structure very carefully so that you don't cause a collapse or further damage to it. You want to take it apart very methodically, and all of that needs to be well planned, so it will take many, many years to do that.
As the dismantling process may take over 100 years, the surrounding structure and the machinery need to be able to withstand not only the high levels of radiation, but any corrosion caused by humidity. The area most at risk is the giant metal framework. Unlike the stainless steel cladding that surrounds it, this is made from carbon steel, which, if left untreated, could be prone to rust.
So on a typical steel building, you would probably have to do a lot of maintenance of the steel to maintain its corrosion resistance. And here in this structure, we just don't have the opportunity to do that. You have the radiation conditions, you have this huge volume, so it was very important that the structure itself be able to resist corrosion for the design life of the arch.
But what can they use to protect this essential structure from decay? It's an issue that's been faced in the past.
Yeah, great day to be on the water.
Engineer Dan Dickrell is in Maryland in the United States, discovering how the US Navy countered their own corrosion problem, to see if it holds any clues for the Chernobyl team.
So this is actually a very surreal scene, these jutted remnants of wooden ships sticking up the Potomac River here in Mallows Bay, home of the largest shipwreck fleet in the Western Hemisphere, sometimes called the Ghost Fleet.
When the US entered World War I, hundreds of wooden vessels were specially built to help the Americans get across the Atlantic.
The problem with the war being over, there was no use for them. So ultimately, they were just left to slowly decay in the environment.
It was a huge waste of resources. So, at the end of World War II, they weren't going to make the same mistake again. And a plan was formed to put almost 1,000 steel ships into storage.
How do we keep these ships preserved for future use? How do you keep the steel from corroding and oxidizing in a saltwater environment? Well, that required a technological solution. Luckily, one man had the answer.
American chemistry professor Walter A. Patrick patented a method to process silicon, a chemical element found in sand, to mass-produce silica gel, a substance which had a quality needed by the US Navy. Which may also help the team in Chernobyl.
This is the USS Iowa, an excellent example of a battleship from the Second World War. She entered service in 1943, saw active combat duty, but was decommissioned shortly thereafter and placed into reserve. If you look at her, she's in amazing condition, very well preserved. How is that possible? For a 75-year-old, she looks great. Well, it's all down to this stuff right here, silica gel.
Each silica particle is covered in pores, which water molecules are attracted to. Once all these spaces are taken, it can't hold any more water. But there is a solution. When silica is heated, the water is driven off, and it can start trapping water again.
Silica gel plays a huge part in everyday life, keeping food, electronics, and clothing free from moisture.
It's also a crucial component of the system used to preserve this ship. Desiccant dehumidifiers draw moist air over a rotating wheel of silica. This attracts the moisture, allowing dry air to be circulated. When the wheel turns, the waterlogged silica is exposed to a heating element. The water detaches and is drained away, and the dry silica can start the process again. By installing dehumidifiers on the mothballed ships, the Navy engineers were able to lower the humidity and prevent them from rusting.
Oh, this is the old communication center. All this stuff is very sensitive to moisture. Still in actually really good shape.
Thanks to silica, the reserve fleet was kept in great condition and ready for speedy reactivation. In Chernobyl, engineers have taken the same method and implemented it on a grand scale.
The ductwork you see brings in air that comes in from the outside and is forced through the dehumidifiers, which then reduce the moisture content of the air. The key component, the actual drying material, is silicon.
This monumental system recirculates almost 500,000 cubic meters of air every hour to maintain 40% humidity, a condition under which carbon steel does not corrode.
If this system weren't here and operating, then the structure of the arch could be subject to corrosion over a period of years.
The dehumidifiers are the final historic piece of the jigsaw that makes this modern engineering dream a reality. The new Safe Confinement has been safely constructed on one of the most contaminated pieces of land on the planet.
Well, I feel very inspired, slightly humble and very proud.
It takes a lot of human ingenuity, a lot of good engineering design, a lot of very thoughtful planning, and always, always attention to safety.
The unprecedented and ambitious project stands as testament to the Herculean effort of a truly international team.
It's an immense example of what the international community can do when they all pull together with a shared objective.
I think being a part of that legacy really gives me a feeling that I have contributed something to the people of Ukraine, to the people of Europe, and perhaps to the people of the world as well.
By building on the work of the inspirational pioneers of the past, upscaling and breaking new ground themselves, the engineers have succeeded in making the impossible possible.